Hello everyone, my name is Miriam and my talk is about the effect of noise level statistics and dynamic range compression on noise adaptation. Noise adaptation is defined as the improvement in the speech reception thresholds when words are delayed from the noise onset, or as the increase in the amount of recognized words when they are delayed in the noise. The physiological mechanisms responsible for noise adaptation are uncertain, but it has been hypothesized that neural dynamic range adaptation can be responsible for it. Here we have the rate level function for an auditory neuron when tones are presented in white. And here we have the response when tones are presented in noise. And you can see that the neuron has shifted its dynamic range toward the noise level. And here we have the response when the noise level is higher, and you can see that the shift is greater. We have hypothesized that this neural adaptation can enhance the speech envelope as represented at the auditory nerve fiber and facilitate speech noise recognition. In addition, it can also facilitate the encoding of speech spectrum. Here you can see that when neurons are not adapted, the spectrum peaks cannot be encoded, but when the neurons have adapted their dynamic range, the speech spectrum is better encoded, and the time course of this neural dynamic range adaptation is similar to the time course of noise adaptation in speech recognition. But not only the mean level of the noise is important for noise adaptation, but the noise level distribution could be also important. Here we have a noise level distribution where 80% of the levels are around 50 dBSPL, and you can see that neurons adapt to that level. But when the noise has uh, around 50 dBSPL the 40% of the time and 70 dBSPL around the other 40%, some neurons adapt to one level and other neurons adapt to the other level. So if dynamic range adaptation depends on noise level statistic and it is responsible for noise adaptation, then we will expect that noise adaptation depends on level statistics. To test this hypothesis, we have measured speech reception threshold for words in noise in four conditions. In one condition with a precursor, in other condition with a steady precursor, with a mildly fluctuating precursor, or with a very fluctuating precursor. The hypothesis is that when the noise level is very fluctuating, neurons will not have a most common level to adapt, and no noise adaptation is expected. And here we have the amount of noise adaptation for 15 normal hearing listeners, and you can see that adaptation is greater for the stationary noise than for the fluctuating noises. So we conclude that noise level distribution is important for noise adaptation. In addition, we have also hypothesized that instantaneous amplitude compression can facilitate noise adaptation. When we have this noise distribution, where the noise is very fluctuating, no adaptation is expected. But when we compress the stimuli by amplifying low sound levels and attenuating high sound levels, the noise distribution will be like this. And adaptation is expected. To test this hypothesis, we measure adaptation for three types of precursors: a fluctuating precursor without compression, a fluctuating precursor compressed with a compression ratio of 2 to 1, or with a compression ratio of 4 to 1. And you can see that adaptation increases as the amount of compression also increases. In addition, we have found that the amount of noise adaptation is greater for cochlear implant users that have narrower electrical dynamic range. So, in summary, we conclude that instantaneous amplitude compression facilitates noise adaptation. The next experiment that we're going to do is to aim at investigating noise adaptation in hearing impaired listeners. The hypothesis is that listeners with other hair cell loss will show less of absent noise adaptation. This is because in the healthy auditory system, we have cochlear compression. So a fluctuating noise turns into a less fluctuating one at the cochlear output. But when the listener has other hair cell loss, there is no compression at the cochlea, so the distribution at the cochlear input is similar to the noise level distribution at the cochlear output. And because the noise is fluctuating, no adaptation is expected. The second experiment that we are going to do is aim at investigating if fast-acting hearing aids reinstates noise adaptation. The idea is that with fast attack and release times, the noise level distribution will be wider at the input than at the output, but when the attack and release times are longer, the distribution will be the same at the input and at the output because the hearing aid will work like a linear amplifier. So adaptation is expected for the fast-acting compression hearing aid, but not for the slow-acting compression hearing aid. Here we have the preliminary results for normal hearing listeners. Here we measure adaptation for stationary precursors or for a fluctuating precursors compressed with instantaneous compressor, fast-acting or slow-acting compressor. And you can see that adaptation is greater with the instantaneous or fast-acting compressor than with the slow-acting compressor, consistent with our hypothesis. Thank you very much.